This is Chapter 3, Control Volume Analysis, Part 11. In this video, I'm going to discuss the concepts of hydraulic grade line and energy grade line. What these are graphical representations of the energy components in their Bernoulli equation. And over here on the right, I've shown an example. Now this example I'm going to discuss in substantial detail in the coming slides, but just to give you a sort of a brief overview, what hydraulic grade line and energy grade line are is they're graphs of the energy components where the horizontal axis is distance, so distance through the piping system, and the vertical axis is the energy content of the flow. And so in this way, you can see, by plotting these lines, you can get some insight into the energy transformations that happen through the piping system. So in this video, what I'm going to do is I'm going to start by defining what the hydraulic grade line is, what the energy grade line is as well, and then I'm going to apply these concepts to a couple of examples. I'm going to start with simple frictionless Bernoulli type flows. So remember that the Bernoulli equation applies to flows that are inviscid, have no viscosity, no energy losses. They're not completely realistic flows. And then I'm going to apply these concepts to real flows, so flows with head losses, flows with pressure losses down the pipe. I'm going to show how you can apply it to flow across a valve and even flow through a pump where energy is added. So in other words, we're going to apply the concepts of hydraulic grade line and energy grade line to flows that are described by the steady flow energy equation that you learned about in a previous video. Now you'll notice that in the textbook these concepts are presented quite early in Chapter 3. Hydraulic grade line and energy grade line are in something like section 3.2. But I've delayed the presentation of these concepts until late in the chapter because I think it makes more sense once you understand the steady flow energy equation. Before we go on to talk about the concepts of hydraulic grade line and energy grade line, I just want to do a little bit of review. I want to talk about the Bernoulli equation again, and in particular I want to talk about this form of the Bernoulli equation. In this form, as you may recall from a previous video, each of the terms has the units of height in either meters or feet, and we call this head. Now recall that head is the energy content of the flow per unit weight of the flow. So energy content in joules, so Newton meters, divided by the weight of the flow, newtons, and you'll, of course, the newtons cancel out, and you just end up with meters. So we can represent the energy content of the flow as a height, and this height we call head. So the first term, v squared upon 2g, of course that's the kinetic energy per unit weight. We call this the velocity head, again expressed as a height. P upon gamma is the flow work done by pressure. Sometimes I call it pressure energy, and this would be P upon gamma would be the pressure energy per unit weight of the fluid, called pressure head, again in meters. And then Z is just a measure of the elevation, the potential energy of the flow. So we call it, of course, per unit weight, so we call it elevation head or just head. Now in a Bernoulli flow, the kinetic energy plus the pressure energy plus the potential energy all add up to a constant along a streamline. Remember, Bernoulli's equation applies to frictionless flows or inviscid flows, flows without any viscosity, so there's no loss. So the energy content along a streamline remains constant. So now we can get to the definitions of hydraulic grade line and energy grade line. And what I've done here is I've reproduced the form of the Bernoulli equation that we're going to use. In this form, each of the terms has units of meters and can be interpreted as a head. As I mentioned in the introduction, hydraulic grade line and energy grade line are graphical representations of the energy components of the Bernoulli equation. And so here on the right hand side, what we're looking at is flow in a pipe. And what we're plotting here is on the horizontal, we're plotting, of course, the distance along the pipe, and then the vertical axis is the head, or the energy content of the flow per unit weight. Now, the hydraulic grade line is defined as a plot of the height of the pressure head plus the elevation head. So Z, which is the elevation head, or the potential energy of the flow per unit weight, is plotted relative to some arbitrary reference point. So we can just arbitrarily pick some point that we call Z equals 0, a datum. But the pressure head, the P upon gamma, is plotted relative to the center line of the pipe. So you can see over here of 0.1 right there. We use the center line of the pipe because in these types of flows, we're representing the flow in a one-dimensional approach. So there's really only one coordinate, that's the distance along the pipe, and so the pressure in the pipe is taken as the pressure on the center line of the pipe as a suitable representative value. It's interesting to note, and perhaps helpful in terms of understanding this, that the hydraulic grade line is the height that a fluid would rise to if you had a piezometer attached to the pipe at that location. And for that reason, it's sometimes called piezometric headline. I mention this because it's maybe easy to remember the definition that way, that hydraulic grade line is the height that the piezometer would rise to if you had one attached to the pipe. And the diagram here over here shows this. At point 1, you can see that the hydraulic grade line passes through the top of the fluid in the piezometer at point 1, and the same thing over here at point 2. So the hydraulic grade line at point 1 is Z1 plus P1 upon gamma, and the hydraulic grade line at point 2 is Z2 plus P2 upon gamma. In contrast, the energy grade line is a plot of the total energy content. So it's really a plot of their Bernoulli constant. So it's the sum of the velocity head, the pressure head, and the elevation head. For an inviscid flow, or a frictionless flow, like we would assume when we're applying Bernoulli's equation, the energy content on a streamline is constant, and so the energy grade line is a horizontal line. We have no energy losses due to friction, due to viscosity, and we have no energy additions, for example, due to a pump in the system. So the energy grade line at point 1 and point 2, and in fact all points in between, is just a constant. It's equal to Z1 P1 upon gamma plus V1 squared upon 2G, and that's the same all the way across. Because the energy grade line's a constant in this kind of flow, it's not very helpful. It doesn't give you very much insight into what's going on. You'll find, and we're going to discuss this later in this presentation, that energy grade line is a more useful descriptor for real flows, those with viscous losses pumps. In other words, for flows where the flow can be described using the steady flow energy equation that you learned about in a previous presentation in Chapter 3. Now I'll ask a question. Why does the hydraulic grade line here, what we're talking about is the hydraulic grade line, why does it increase in the flow direction? You might want to pause the video at that point and just think about this. I'm going to give the answer in just a second. the answer is because the difference between the energy grade line and the hydraulic grade line is the velocity head. So you can see here the difference at point 1 between the hydraulic grade line and the total amount of energy is just the velocity head, the kinetic energy per unit weight. And the same thing's true over here at point 2. That's the difference between the energy grade line and the hydraulic grade line. And what's interesting is in this flow, you can see that the pipe diameter is gradually getting bigger in the flow direction. That means that the velocity is going to be decreasing. The average velocity will be decreasing because of continuity. So you'll have less kinetic energy in the flow as you move downstream, and so the hydraulic grade line will approach the energy grade line. Basically what's happening is you're converting kinetic energy into pressure energy. You're converting velocity head into pressure head as the flow moves downstream. So I hope that makes sense. And so that's the definition of energy grade line and hydraulic grade line. And what we're going to do now is move on and do some examples. The first example I'm going to consider is Inviscid, or frictionless flow through a Venturi meter. And you've seen this kind of device before in some of the other videos in Chapter 3. A Venturi meter can be used to measure the flow rate in a pipe. Basically, you have a constricted section in the pipe here, and because of continuity, the velocity of the fluid in the pipe will increase as the cross-sectional area decreases. And from the pressure difference between point 2 and point 1, you can deduce the average velocity in the pipe and the volume flow rate. So what we're going to do now is look at this kind of device that you're already familiar with and plot the hydraulic grade line and the energy grade line, just to illustrate how this graphical approach works. As I mentioned, the heights of these curves in both cases represents the various energy contents of the flow per unit weight. As we discussed on the previous slide, the hydraulic grade line corresponds to the height that a piezometer would rise if there was one attached to the pipe. So it's Z plus P upon gamma, the elevation head plus the pressure head. And here at point 1, you can see this is the point that a piezometer would rise to, Z measured relative to some arbitrary reference, plus P1 upon gamma. Now, the hydraulic grade line here remains constant until we get to the section of the pipe where the cross-sectional area decreases. And when the cross-sectional area decreases, the average velocity of the flow increases because of continuity. You're going to have more kinetic energy, which means you must have less pressure head. So you gain velocity head at the expense of pressure head. And so the pressure at point 2 decreases. We have a minimum pressure at the throat, and indeed a piezometer would rise to a much lower height because of the low pressure. The energy grade line here for this type of flow, since we're considering frictionless flow, is just a constant. It's the summation of the elevation head, the pressure head, and the velocity head, if we assume there's no losses. And the difference between the hydraulic grade line and the energy grade line is just the velocity head. And so we have a small difference here at the inlet, and when the velocity increases, we get a maximum velocity at the throat, we get the maximum difference between the energy grade line and the hydraulic grade line. Now I'll point out that this is an ideal Inviscid flow, and so if the pipe diameter at 1 was the same as the pipe diameter at 3, you'd have the same average velocity, and so the pressure would decrease toward the throat, and then you'd get complete recovery. So the height of the hydraulic grade line at point 1 would equal the height of the hydraulic grade line at point 3. in an ideal frictionless flow. In this type of flow, you'd have no pressure losses. Of course, in reality, as a fluid flows downstream, you will get pressure losses. So in real flows, the pressure at point 3 will be somewhat lower than the pressure at point 1, and the hydraulic grade line won't recover completely. So the piezometer will have a smaller vertical deflection downstream. And we're going to talk about that in some of the next examples, which consider non-ideal flows. So next we're going to consider actual flow through a Venturi meter. So unlike the previous example, this is a real viscous flow. And this is actually a preview of what you're going to see in lab number 4, which is the Venturi meter lab. And so here's a picture of the apparatus from lab number 4. There's a water flow from left to right. And in this experiment, there's a piece of plexiglass on the side of the Venturi flow meter so that you can see the cross-sectional area. You can see the cross-sectional area gets reduced gradually to a minimum here at what's called the throat, which is the point of maximum velocity. And then as the flow moves downstream, you can see that the cross-sectional area of the flow increases and the velocity will decrease in this region. There's also 7 piezometers here, and so we can actually make a measurement of the hydraulic grade line, see how high the fluid rises in those piezometers, and compare that to what Bernoulli equation would predict for an ideal Inviscid flow. And that's one of the objectives of the lab. But it's nice today to show this in order to explain the concepts of hydraulic grade line and energy grade line for actual flows. This is the experimental setup for lab number 4. You can see the Venturi flow meter at the bottom with flow from left to right. So on the left-hand side, there's this blue water tank, and there's a supply of water continuously to that tank. And the pipe that you see up here is actually an overflow pipe. So there's water coming into the pipe, and so the water level in this tank will be somewhere up around here, and there'll be a continuous overflow. You can see the Venturi meter there attached to the bottom of the water tank. There are, as I mentioned, 7 piezometers, and in this case I've added a little bit of blue dye to the flow just so you can see the heights of the piezometers. When you do the experiment for lab 4, there won't be any dye. And there's a valve here, just a hand valve on the outlet that allows me to control the flow rate through the system. Next, I'm going to show a short video presentation of lab number 4, the Venturi flow meter. And after I've shown this video, we're going to look at the analysis of the hydraulic grade line and the energy grade line for this actual flow. Now, before I start the video, you'll notice here that there's no flow through the Venturi at the moment. This valve over here is closed, and so all of the piezometers here have fluid at the same height. They would be at equilibrium with the fluid in the tank, and so that represents the fluid level in the tank at the start. So now let's just watch the video. So at the beginning here, I'm just opening that valve to let some flow through, and you'll notice the piezometer levels changing dramatically. Now you can see it's pretty much at steady state. So you're seeing the steady state hydraulic grade line. Finally, what I'm going to do is just turn the flow back down, turn it off. And there it is with the flow off, and we're back to the original situation. So now there's no flow through the Venturi flow meter, and all of the piezometers are back to the original level, the height of the level in the adjacent tank. And you can see that because I drew a little bit of flow, the height of the water level in the tank has decreased slightly. So next what we're going to do is analyze the results of this. I'm going to describe the hydraulic grade line and energy grade lines using those piezometer results. This is a screenshot from the experiment showing roughly the steady state piezometer levels. And in this experiment, the water level in the tank would be approximately here. And so you can see the piezometers are all lower than the water level in the tank. The heights of each piezometer indicate the local pressure. So it's P upon gamma, where gamma would be the gamma of water and P would be the local pressure. And so we can get the hydraulic grade line by just simply joining the fluid levels in the tops of the piezometers. And you can see that the minimum pressure here, or the minimum in the hydraulic grade line, is at the throat of the Venturi meter, where you have the maximum velocity. So what's happened is you've gained kinetic energy, you've gained velocity head at the expense of pressure head. I'll also point out something interesting. And in contrast to the ideal flow in a Venturi that we talked about earlier, you don't get complete recovery of the pressure head. So the heights of the piezometers for the first and the last piezometer are not the same, even though the cross-sectional areas of the Venturi meter are the same at those locations. This is an indication that you've got some losses in the system, some energy losses. So pressure is decreasing in the downstream direction. You're losing some pressure head because of, well, viscous losses and because of turbulence. And so now when we draw the energy grade line on the diagram, you can see that it slopes downward in the flow direction. This is because of energy losses associated with viscosity and turbulence. At the tank side here, the velocity is approximately 0, and so the energy grade line and the hydraulic grade line coincide. Remember, the difference between the hydraulic grade line and the energy grade line is the velocity head, v squared upon 2g, which is 0 at the tank, and it's a maximum. You get the maximum difference where the velocity head is a maximum, which is at the throat here. Okay, I'm going to end with a discussion of hydraulic grade line and energy grade line for what I'll call a complex piping system. So what we have here is a large tank that's feeding flow into a pipeline, and this is not drawn to scale, of course. We might have a very long pipeline to the point where you need to increase the pressure in the pipeline using a pump in order to get the required flow rate. And then most piping systems would have many valves. I've just drawn one valve here. And the pipe ends in a nozzle and a high-speed fluid jet. And so the task here is to draw the hydraulic grade line and energy grade line for this type of system. And so here they are. The upper line, the dashed red line, is the energy grade line, and the lower solid red line is the hydraulic grade line. As in all the previous cases, the height of the hydraulic grade line above the center line of the pipe, so above the center line, the height here is just the pressure head, P upon gamma. And of course we have some arbitrary datum here, our elevation head, which really doesn't play a role in this case because we have a horizontal piping system. Now in all cases, as before, the difference between the energy grade line and the hydraulic grade line is just the velocity head, v squared upon 2g. And so back in the tank here, at the tank, where the velocity is about 0 or very low, the hydraulic grade line and energy grade lines are the same. Now in this case, both the energy grade line and the hydraulic grade line slope downward in the flow direction because of energy losses. As I mentioned, these energy losses are because of viscous effects, viscous friction, viscosity, and because of turbulence. Now, if you had a long piping system, you wouldn't have enough head from the tank to drive the flow, so you'd need a pump. And the pump, as we learned in previous videos, adds energy, so we would have the head of the pump being added to the flow at that point. And moving further downstream here, most piping systems have valves. You probably have a valve on each side of the pump in order to isolate the pump. I've just drawn one here. When flow passes through a valve, it passes through a complex path, not a smooth path through the pipe. And so there's some energy losses associated with that, associated with turbulence. And so you'd have some energy losses, the head loss from the valve. And finally, at the end of the pipe, the nozzle converts all the remaining pressure head into velocity head. And so the hydraulic grade line falls all the way to the center of the pipe. So it's 0 at that point relative to the center line of the pipe. This is about as complex as these hydraulic grade line and energy grade line problems get. If you understand this one, you've probably got a handle on this. So as I've done in many of these videos, I'm going to end by just showing something that's completely unrelated to the current topic, but kind of cool and interesting and related to fluid mechanics. This is some high-speed photography showing the incredible complexities of the flow associated with striking a simple match. It uses something called Schlieren photography, which reveals the very small density variations in the fluid. It's about 2.5 minutes long, and it's really, I think, a fascinating video, so hang in there till the end. It gets more interesting as the video goes on. So at this point, I'll just keep quiet and play the video because I think it speaks for itself.